All right, so today we're going to be introducing the notion of concavity. We'll be going over how to sketch some functions that aren't obvious what they look like. And then the third section we'll cover today will be another one of those sections where it just introduces more complex problems, not really teaching you anything new. Okay, so that's a big picture of what we're doing. So, first, we're going to talk about where functions are increasing and decreasing. So, what do we mean by that? Going left to right. So let me just draw some function. Going left to right, the function's decreasing here, not increasing or decreasing here. Now it's increasing. Neither, now it's decreasing, etc. Right?
Yeah.
So notice that where it's decreasing, the slope is negative. So the derivative is negative.
Yeah.
So a negative derivative indicates that the function is decreasing there. And a positive derivative indicates that a function is increasing there. So if the derivative of the function is greater than 0 on some interval, f is increasing on that interval. Make perfect sense?
Yeah.
Similarly, if f prime of x is less than 0 on some interval, then f is decreasing on that interval. Make sense? Let's do a quick example. So, see the example problem they have for us. Find the critical points of this function and figure out where it's increasing and decreasing. Okay, so f of x is equal to x cubed minus 12x, just 12x minus 5. So here's our function. Go ahead.
To find the critical points, isn't that just to find the absolute values?
No, that's to find where the derivative is 0, and then we also included, just where the derivative is 0 or undefined.
That's right.
So notice that where the slope changes from being negative to positive, it first has to go through a critical point, a place where the slope is 0. So that's why we're interested in critical points, because the function may or may not go from increasing to decreasing at a critical point.
I see.
So there's f of x, f prime of x is equal to 3x squared minus 12, right?
Mm-hmm.
Which is equal to, just factor 3 out of these. Right?
Okay.
Which is equal to 3 times x minus 2 times x plus 2. Okay. So we can see our critical points, our place where our derivative is 0 is going to be when we plug in 2 or minus 2. Right?
Mm-hmm. Yeah.
So those are the points that we're interested in. So from here we typically draw a little diagram like this, marking our critical points. So we have a critical point at negative 2, and we have a critical point at 2. The question is, what is the function doing in between these points? What does the derivative look like in between these points?
Okay.
You with me? I know it's
Yeah.
0 at this point, so let's figure out what the derivative is like in between these points. So if I plug in a number like negative 3, how does my derivative come out? Positive or negative?
Well, that's negative 5 times negative positive.
Positive. So over here I know my derivative is positive. So I know my derivative is positive from negative 2 to infinity.
Okay.
Because the only way my derivative could go from positive to negative is if it's first 0. And I've identified all the places where my derivative can be 0.
How about where it's undefined?
It's not ever undefined. That's polynomial.
Oh, I see.
So I know from negative 2 to infinity, this function is increasing.
Mm-hmm.
So now let's look in between here. Plug in a number like 0, what do we get?
A negative.
We get a negative. Right?
Yeah.
Finally, plug in a big number over here, like 3, what do we get?
Positive.
Positive.
Yep.
So I know that this function is increasing from negative infinity to 2, or to minus 2. I know it's decreasing from negative 2, we can use square brackets. Doesn't matter if you include the point or don't include the point, the endpoint, because it's not increasing or decreasing exactly at -2.
Okay.
So we can go ahead and not include that point if that makes you feel more comfortable.
Okay.
But you can also include it.
Okay.
So -2 to 2 is decreasing, and then finally it's increasing from 2 to infinity. So I think that's what this problem wanted us to find. Let me read it one more time. Find the critical points of f of x and identify the open intervals on which f is increasing and on which f is decreasing. Okay, so it specifically said the open intervals. So we did that, because these are all open intervals.
Okay.
Okay, and then just a real rough idea of what this function would actually look like, just to help get some closure across the board. Let's see. When I plug 2 into this function, what do I get? 8 minus 24, right? Did I do that right?
Mhm.
Which is minus 12. Am I doing that right? 8 minus 24.
29.
8 minus 29, so minus 21. And then, let's see, that was at 2. So at 2, we're down here at minus 21. And then when we plug in -2, so somewhere over here, we get what? -2, we have -8 plus 24 puts us at 16, minus 5 puts us at 11. Right?
Mm-hmm.
So whatever this looks like, from -infinity to -2, it's increasing. So it must be down here to increase. So it's coming up, and then it starts decreasing until it reaches this point, and then increasing after that. So very, very rough sketch of what it looks like.
Okay.
Make sense? So this is part of what you're going to be doing in the next section. You're going to be given a function, and your job is to reconstruct what the function looks like, roughly. So this is a piece of what we'll do to help reconstruct the function. We'll do some other stuff as well to get a better picture. Okay, let's do another example. Oh, point out a fact, then do another example. Notice that if we're talking about a local max, a local max kind of looks like the top of a hill, right? Here's what a local max looks like on a function. Then maybe it comes down and then we have a local min down here. There's what a local min looks like. Notice, to the left of a local max, so if we're looking at a point over here, what's the derivative? Positive or negative?
Positive.
Positive. And if we look to the right, what's the derivative?
Negative.
Negative. So if, that's this one, if f prime of x changes from positive to negative at some point c, then f of c is a local max.
Okay.
Make sense?
Mm-hmm.
Yeah.
Similarly, notice right here the derivative is negative, and right here the derivative is positive. So if the derivative changes from, if f prime of x changes from negative to positive at c, then f of c is the local min. Make sense?
Mm-hmm.
Okay. So next one, find the critical points of this, identify the open intervals on which f is increasing and decreasing, find the function's local and absolute extreme values. Okay. So our next function, f of x, is equal to x to the 1/3 times x minus 4? 4. Okay. So here's f of x. I'm just going to distribute that through. So that's x to the 4/3 minus 4x to the 1/3, right?
Mm-hmm.
Does it give me a domain? No, it doesn't give me a domain. Okay, so I was wondering if we were going to have to check endpoints of our domain for max and min, but we're using all real numbers. Okay. Anyways, so now f prime of x, what's that equal to?
4/3 x to the 1/3 minus 4/3 x to the negative 2/3.
Perfect. So there's f prime of x, right? I'm going to factor a 4/3 x to the minus 2/3 out of the whole thing. So that's going to give me x minus 1.
I don't see how you did that.
So x is the same thing as x to the 1, right?
Yeah.
When you multiply terms, you add exponents. What's negative 2/3 plus 1?
1 plus 1 to the 2. 1 2/3.
1/3.
1
Negative
plus
2/3. Negative 2/3
Oh,
plus 1
okay.
is equal to 1/3. Or 1 minus 2/3 is equal to 1/3. Right?
Mm-hmm.
Okay, so when you multiply that to that, you get this term. And then obviously when you multiply that to minus 1, you get this term.
Okay.
Oh, I see how you did it.
Okay, and just to write it one more way to make it very clear what this looks like, we have 4x minus 1 all over 3x to the 2/3, right?
Yeah.
Okay, so our critical points then are at 1 and at 0. 1 is where the derivative is 0. 0 is where the derivative is undefined.
Mm-hmm.
So those are our two critical points.
Okay.
Can you go over that? The 1, I see the undefined, but
Plugging 1 into the function, what do you get in the numerator?
0.
oh, 0.
Okay. Remember, where you're checking where a fraction is equal to 0, you just care where the numerator is 0. So completely ignore the denominator where you're wondering where is this equal to 0.
I see.
Unless it happens to be undefined at that same point that makes the numerator 0. Anyways, okay, so let's draw our little number line. We know 0 is a critical point and 1 is a critical point. Let's see what this derivative is doing in between. Make sense?
Mm-hmm.
So let's plug in negative 1, see what we get. Negative 1, do I get a positive or a negative?
Negative. Right?
Yeah, negative.
Yeah. The denominator is always going to be positive, so our numerator is all we really need to check.
Why is the denominator always going to be positive?
Because you got to square the thing.
Oh, I see.
Okay, so when we plug in 1/2, is it positive or negative?
Negative.
Negative.
Yep.
So notice that at 0, it didn't switch signs. So it doesn't necessarily switch signs at our critical points.
That's because it's undefined.
The function
right?
was decreasing, the function was decreasing.
Okay.
No, the derivative, this could also happen if it were defined there, just 0 there. That can also happen.
What does
Yep.
it look like?
We talked about this yesterday. Cubic is an example. It has a derivative of 0 right in the middle. So, positive, 0, positive.
Okay.
Anyways, now plug 2 into it, what do we get?
A positive.
A positive. So this thing is negative, 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 undefined, negative, positive. And what else were we supposed to do? Find the max and the min of this thing.
Alright.
So if it's decreasing and decreasing, so it's coming down, then it must go off to
Infinity.
infinity in the right, and it's always increasing this way, so it goes off to infinity to the right. So this thing doesn't have a max, and the min is going to be at whatever 1 is.
Why 1? Why not 0?
This is where the derivative is 0, right? And notice that you have negative slope on its left-hand side and positive slope on the right-hand side.
Oh, I see.
So this is going to be our minimum. So no max, and our minimum is going to be at f of 1,
Okay.
which is, what is that? Yeah, you do. You're plugging in 1,
Minus 4, so negative 3.
negative 3.
Okay.
1 to the 4/3 is just 1. Cubed root of 1 is just 1. So 1 minus 4, minus 8.
Okay.
Okay, so we found everything that they did. Rough sketch of this thing to give you a sense of what's going on. Oops, forgetting some at the bottom to get -3. So -1, -2, -3, then whatever. So we know that when we plug in 1, we got -3. So it goes from this point, right?
Mm-hmm.
Really quick, let's plug in 0 to see exactly where that lands. When we plug in 0, what do we get? 0. So our function, roughly, is going perfectly vertical slope right there, comes back out, and then increasing this way. Something like that.
Isn't 0 undefined though?
The derivative's undefined there.
Oh,
So it's got a perfectly straight down slope.
so it goes straight vertical?
Straight vertical for a second.
Is that what undefined is?
Not always, but that's one way to do it.
Okay.
So there's roughly what it looks like. So you can see when it has no max, and yep, that's the min. All right, next. Unless there's any questions on this one.
No.
Makes sense.
Okay.
I would like to clarify fractions. So how do you solve x to the 4/3 again? In your head?
You're saying for a number?
Yeah.
So when you plug in a number, you either take its cubed root first, and then raise it to the power of 4.
Okay.
Or you raise it to the power of 4 first, and then take its cubed root. Doesn't matter the order. So for example, if I say 8 to the 2/3, or 8 to the, that's 4/3. Well, the cubed root of 8, let's just be a bit pedantic here. I can always rewrite like that.
Okay.
Okay? So now that's 2 to the 4 is 16.
I see.
So that's what that's saying. Okay, anyways. Our next one looked like we were using some trig functions. So our next function is sine squared of x minus sine of x. And I think there's a constant, minus 1. This is on the interval 0 to 2 pi, I think, including 0 to 2 pi. Okay, yes. So identify the open intervals on which f is increasing and on which f is decreasing. Find the function's local and absolute extreme values.
All the local?
Yes.
Okay.
So all the local maxes and mins and the absolute max and min. Okay. Because whatever this looks like, it's going to have some sort of sine functionality to it. So we expect a lot of waving back and forth. So lots of max and mins. Well, a few. Let's figure this out. Okay, so f prime of x. What's f prime of x equal to?
Cosine squared of x.
No.
2.
Chain rule.
Yeah.
2 times
Cosine x.
times sine of x
Times sine of x, yeah.
times
Cosine.
cosine of x, the derivative of the inside.
Where'd the...
Look, this is the same thing as sine of x squared, right?
Mm-hmm.
Yeah.
So, if you think about u is equal to sine of x, what's the derivative of u squared? It's equal to 2u times du dx. Right?
Okay.
Same thing here. So we have sine squared, so if we have sine squared, I shouldn't say this is equal to this, the derivative of this with respect to x is equal to that. So now if we're doing the derivative with respect to x of sine squared of x, that's going to be equal to 2 sine of x times the derivative of sine of x with respect to x, cosine x.
Okay.
Follow that? Good?
Mm-hmm.
Same old stuff you've been doing over and over and over again. Okay, minus, impress me.
Cosine of x.
Oh, So you don't even have to look at your cheat sheet, okay? We'll factor out cosine of x from both of those, and so we'll get cosine of x times 2 sine of x minus 1, right?
Yeah.
Okay, so where is this 0? F prime of 0 is where this is 0 or where this is 0,
Okay.
right?
Yeah.
So our critical points. First off, where is cosine of x equal to 0? On this interval, 0 to 2 pi.
So,
2 pi.
pi halves.
Pi halves, sorry.
Pi halves and
And 3 pi halves.
perfect. Okay, so now we need to look at where this is 0. So I want to know where is 2 sine of x minus 1 equal to 0? Or in other words, where is sine of x equal to 1/2? Bring the 1 over, divide both sides by 2.
So it's like
It's like what? Where is sine 1/2? Remember, sine's your y coordinate. Where are you up 1/2?
pi quarters.
No, that's root 2 over 2.
You're right.
It's pi 6.
Pi 6 and
And
on the other
5
side now.
pi 6.
5 pi 6, perfect.
That's it.
Okay, so those are our 4 critical points. Now we gotta figure out if those are maxes or mins, and which one's the absolute max and which one's the absolute min.
Okay.
Okay, so plot these on a line. Let's see, we'll put our 0 and 2 pi on here. Just remember, we're now defined on a closed interval, so our max and min could also be at these points.
Yeah.
So remember, you gotta check your endpoints when you're given a closed interval when the function is defined on a closed interval. So we gotta check 0 and 2 pi. Let's see, we need to check next number is gonna be pi 6. And then we'll have pi halves. This isn't in any way to scale. And then we'll have 5 pi 6. And then we'll have 3 pi halves. Something like that, right?
Mm-hmm.
So we need to check in between each of these to see what the derivative is doing.
Okay.
Figure out if it's increasing or decreasing between these. So for a number less than pi 6, slightly smaller than pi 6, what do we get? Cosine is still positive, but now sine of x will be slightly less than 1/2.
So it's a negative.
So this will be slightly less than 1, so when you minus 1, you'll be a little bit negative.
I'm confused on how you're getting that.
So, unit circle,
Mm-hmm.
here's pi 6. Right? We know that this height is 1/2.
Yeah.
So now let's look at a point like right here. What's the height there? Less than 1/2. Something like 1/3, who knows?
Okay.
So, if sine of x is less than 1/2, 2 sine of x is less than 1.
I see.
So something less than 1 minus 1 comes out negative. So this term is negative.
How do you-
Cosine is still positive
How do
because
you
it's
know?
over here.
Oh, I see. I see.
And so we get negative here. With me?
Mm-hmm.
Now, if sine of x was something slightly bigger than pi 6, so slightly bigger than 1/2, so now if we go a little bit up here, this whole thing is now positive. Cosine of x is still positive, so we're positive here.
Yeah.
Okay.
With me?
Mhm.
Yeah.
So now we're looking at a little bit past pi halves. So coming up here, a little bit past pi halves.
Makes
Still positive.
Well, cosine's now negative.
Oh, so it is negative.
Cosine's negative. This is still positive. And so, we're negative, right?
Yeah.
Now, checking between 5 pi 6 and 3 pi halves. So carry this over. This is 5 pi 6. So now we're talking about a point right here.
That's going to be positive.
This is going to be negative. This is going to be negative. All together comes out positive, right?
Mm-hmm.
Mhm.
And then finally, talk about a point a little bit over here.
Cosine positive.
Cosine is going to be positive. This is going to be
Negative.
I'm
Negative.
confused.
which one?
When we were doing
This
5
one?
pi 6 to 3 pi half, why did we look at a dot? Never mind, I see now. Right. That's right.
Good?
Yep.
Okay. So there we have it. So we know, where is this thing increasing? This thing is increasing on the intervals pi 6 to pi halves, comma, 5 pi 6 to 3 pi halves. So that's where it's increasing. It's decreasing on the intervals 0 to pi 6 and pi halves to 5 pi 6 and 3 pi halves to 2 pi. Right?
Yeah.
So we found where it's increasing, where it's decreasing.
Okay.
Now we know pi 6, is this going to be a max or a min?
A min.
Right, which points are our max points and which points are our min points? Okay, pi 6, is this a max or a min?
A min.
Is that a min? We're
Oh,
decreasing and increasing?
You're,
Yeah.
yeah.
Yeah, it's a min. So a min at pi 6 or at f of pi 6, right?
Yep.
So that's one of our mins.
Mhm.
It just goes back and forth.
What about pi halves?
Max.
That's going to be a max. So f of pi halves is going to be a max.
It's a min.
5 pi 6 is a min. 3 pi halves is a max.
That's a min.
That's it.
And then that's it. And then we need to check our two endpoints to see if one of them is the absolute max or the absolute min. So we need to figure out what f of 0 is, and we also need to figure out what f of 2 pi is, right?
Mhm.
So let's figure out all these things. What's f of 0?
Just negative 1.
Just negative 1. Plugging back into f now, not f prime. Keep that in mind. F of 2 pi, what's that?
Sine of 2 pi is 0.
Negative 1.
Negative 1.
0 and 2 pi are the exact same point,
Yeah.
right?
Yeah.
Okay. So now, we have those. Let's figure out what these are. So these are equal to, terrible notation, but you get what I'm after. Plug in pi halves, what do we get?
We get 1 minus 1 minus 1, which is minus 1.
So minus 1 is a local max.
3 pi halves.
We plug in
Negative
3
1
pi
plus
halves,
1.
what do we get?
It's also minus 1.
Is it? Negative 1 squared is positive 1, then positive 1,
Oh.
then
So
minus
it's
1, so
positive
it's
one.
positive 1. So f at 3 pi halves should be our absolute max as well, right?
Mhm.
And then this is equal to f at pi 6, what do we get?
Max squared.
Yeah, so we have 1/4 minus 1/2 minus 1, right?
Mm-hmm.
So that's minus 5/4.
Yep.
Minus 5/4, comma, and then f at 5 pi 6 is going to be what?
Same thing.
Same thing. Because sine is still 1/2 and this only has signs in it. Okay,
Doesn't that change it though? Because
so notice that this is our absolute max, and both of these are our absolute mins.
You can have 2 absolute mins.
Yeah. Think about just a sine function.
That's right. So why do those hit negative 1 and those hit negative 5/4? That's not a sine function.
Well, this isn't just a sine function, this is something complex.
Oh, are we gonna graph it?
Well, we can get a rough idea of what this looks like from all the points we just found.
Okay.
So, let's see, f of 0, f of 2 pi, we've got that figured out. Erase that. Try and get our picture right here. Shouldn't need to go more than 1 up, and minus 5/4 down. 0 to 2 pi. So we'll call this 2 pi, which means this pi, which means this 3 pi halves, which means this pi halves, and pi sixth is going to be somewhere over here. Pi 6, 5 pi 6. 5 pi 6 is going to be somewhere right next to pi. Something like that, right?
Yeah.
So I know my function is -1 here. So we'll just put -1 and +1. So it's -1 here at 0. It's -1 here at 2 pi. Let's see. At pi halves, we're at -1. Right?
Mm-hmm.
Oh, pi 6. Where are we at pi 6? Minus 5 pi fourths. So we go down some. Right?
Yeah.
And then pi halves, we're back up there, 5 pi 6. We come back down here. Pi, did we ever plug pi into this thing? Let's just plug pi in really quick to see what we get. When we plug in pi, we get -1, right?
Mm-hmm.
So pi, we get -1. And then at 3 pi halves, we shoot clear up there to +1. Right? So our function is very roughly something like that. So 2 bumps, and then up there.
Why the heck does it do that?
Well, we just drew it as best we could.
Okay.
I mean, we're just plotting points and describing its functionality. Now notice, 0 to pi 6, it's decreasing. So from here to here, it's decreasing. From pi halves to 5 pi 6, it's decreasing. And then from 3 pi halves to 2 pi, it's decreasing. And then increasing from pi 6 to pi halves, and increasing from 5 pi 6 to 2 pi thirds. 5 pi 6, all the way to 2 pi thirds. Or 3 pi halves, not 2 pi thirds.
Okay.
Make sense? So yeah, we were able to roughly figure out what this function looked like with this information. Okay, that's the end of that section. Next we move on to concavity. Concavity. In short, what is concavity? It's the change in the derivative. It's the second derivative. It's the change in slope. So notice that, okay, a function like this has a positive derivative, and a function like this has a negative derivative, right? The slope is positive or the slope is negative.
Yeah.
Now, if it has positive concavity, that means the slope needs to keep increasing. Right?
What do you mean?
The slope is the change in the height of a function.
Yeah.
So positive slope means it's getting higher, negative slope means it's getting lower. Concavity is the change in the slope. So this has a slope. If the slope gets higher later in this function, then it might start to look like that. So it went from, we got more slope. The slope became more positive. If we give this more slope, it might change from this to something like this. It's now less negative. The slope increased. So the slope going from here to here increased. The slope going from here to here increased.
I see.
Good? So in general, concave functions, if it has positive concavity, the function looks like a smiley face. Notice that on this whole interval, the slope is increasing. Starts out really negative, gets less negative, less negative, less negative, less negative, less negative, 0. More positive, more positive, more positive, more positive, more positive.
Okay.
And that's a positive concavity.
Positive concavity. Makes a smiley face. We're happy about the positive. We're sad about the negative concavity. Frowny face.
Are you looking at these for the derivative graph or the...
I'm saying that the second derivative anywhere on this is going to be positive. The second derivative anywhere on this is going to be negative. Because the slope now on this one is getting more and more negative. The slope starts out positive, but it gets less and less positive as time goes on. And now it's 0, and now it's getting more and more and more negative.
Okay.
So the second derivative, I know is always going to be negative on this function. The second derivative, I know is always going to be positive on this function.
All right.
Make sense?
Yeah.
That's in a nutshell what we're talking about. Concavity, the change in the slope. We call this concave up because it has positive concavity, and we call this concave down because it has negative concavity. Concave up functions can hold water, concave down functions cannot hold water.
Okay.
Trying to remember all the little things that I've heard about it to help people remember it. Anyways, now let's get our definition. Let y be some function that's differentiable, so you can take the derivative of it. F, some function f, is concave up, so we're talking about something that looks like this now. F is concave up on some interval I, so the interval that includes this portion of the function. There's I. F is concave up on some interval, provided that the derivative is always increasing. Or in other words, the second derivative is always positive. Same thing.
Okay.
So the derivative starts out very negative right here. This is a very negative derivative, and it keeps getting bigger and bigger and bigger. Less negative, less negative, less negative, 0, more positive, more positive, more positive. Now it's a very big number.
Okay.
Similarly, f is concave down, so now talking about this, on some interval I, provided that the derivative is decreasing on that interval, or the second derivative is negative. So we start with a really positive slope, and then it becomes less positive, less positive, less positive, 0, more negative, more negative, more negative, very negative slope. The derivative is decreasing.
Okay.
Okay, that's all there is to concavity.
What if it's not a parabola?
Well, this is just looking at a slice of the function, right? So, really crude example, really quick. Say I have a function that looks like this, right?
Mm-hmm.
It's going to be concave down from some point here onwards. So this whole thing will be concave down. This portion, however, will be concave up.
Yeah.
And the concavity will be 0 right there, meaning if you take the second derivative and calculate where the second derivative is 0, you'll get that point.
And we're going to calculate these, right?
Uh-huh.
Nice.
Because concavity also helps us. One more point to make for finding local max and local min. Here's another way that we can do it using the concavity. Notice that the concavity of this whole function is positive everywhere on this interval, right?
Mm-hmm.
So if your derivative is 0 at a point, and its second derivative is positive, so it's concave up, you have a min. So now we don't need checkpoints to the left and to the right. We can just check the second derivative at that point also.
I see.
At this point, f prime of x, we'll call that point c. F prime of c is equal to 0, right?
Yeah.
But f double prime of c is equal to some positive number, because this whole thing is concave up. Everywhere here, the second derivative is positive.
So you would find the derivative of f and x, and then the derivative of the derivative of f and x, and then plug c into that to find out what it is.
Yeah, so you find where the derivative is 0, that gives you this point. Then you check the second derivative at that point. If it's positive, you know you have a local min. If it's negative, you know you have a local max. So it's another way of finding a local max and a local min, okay? So that we don't have to check a point to the left and to the right.
Yeah.
See how that makes our life easier?
Yeah, it does.
Now, if it's 0, then that tells us nothing, and we have to check a point to the left and to the right. So you may at times still have to check a point to the left and to the right, but if the second derivative spits out a positive number, we're for sure at a min. If the second derivative spits out a negative number, we're for sure at the max.
You're saying if the second derivative spits out 0?
Yeah, if the second derivative spits out 0, you can't conclude anything.
Why would it ever do that?
Same reason derivatives sometimes come out 0. We'll see examples. But as a general rule, this is how we check it. So we don't have to keep checking so many points. Okay, so first example. The curve y equals x cubed. He's just telling us stuff about it, trying to formulate it as a question. So we're looking at y is equal to x cubed. And I guess we're trying to find where this is concave up and concave down. So y equals x cubed, really quick, let's draw that picture just very roughly. It looks something like that, right?
Mm-hmm.
Now we expect this thing to be concave down on the left hand side, concave up on the right hand side. Right?
So it doesn't have to be
The parabola.
No. So let's do a quick calculation. So y prime, what's y prime equal to?
3x squared.
3x squared. Where is that equal to 0?
When x is 0.
When x is 0, so notice that the derivative is 0 right here. But everywhere else we get a positive number, so this function is always increasing. It's never decreasing. So if we were to plot that, our interest point is 0. If we plug in the number to the left, plug in a negative number, what do we get?
Positive.
Positive. If we plug in a positive number, we get a positive. So this function is always increasing.
Isn't it decreasing
No.
on the
We're
left?
getting bigger and 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 bigger. I'm talking about the function, the value of the function.
Oh, the value.
We didn't talk about concavity yet.
Okay.
So now concavity, that's y double prime. What's that equal to?
6x.
6x. So now when we're talking about the concavity of it, where is the concavity 0?
0.
Also 0. Where is it negative?
Any
Any negative.
Any negative number. So over here is negative, and if you plug in a positive number, it's positive, right?
Yeah.
So that tells us that it's concave down from 0 to, or from negative infinity to 0. So negative infinity to 0 is concave down, and then concave up from 0 to infinity.
Is that the notation for it?
No, I'm just
Oh, okay.
not taking the time to write out words since I'm saying it. Yeah, do not do your homework nearly like this. I will not know what you mean by CD, negative infinity to 0. That tells me nothing.
Okay.
The answer in the back of your book will tell you how you should be giving your answers, if you're wondering. But spell it out. Yeah, I'm being lazy so that we don't waste time. Let's do another one. Determine the concavity of, oh wait, they also did x squared. So now let's look at x squared. We know what x squared roughly looks like, right? Just a parabola pointing up. Something like this. That's terrible, but you get the point. Okay? Y prime is equal to
2x.
2x. Notice that that is going to be negative for negative numbers, positive for positive numbers, 0, 0, right?
Yeah.
So we have negative slope over here, positive slope over here, exactly what we expect. Now let's look at the concavity. What's the second derivative of this?
Just 2.
2, which is a positive number, so it's always positive. So this whole function is concave up, just as we expect.
Okay.
It's one big smiley face. There's no frowning bars. So the whole thing's concave up.
So,
Yeah.
so if it's only going in one direction, the whole function, then it will usually be constant. Concave?
No, because if we did something like x to the 4, that's just a steeper parabola. Now its first derivative is 4x cubed. Same thing, negative for negative numbers, positive for positive numbers. And now its second derivative is 12x squared, which is positive everywhere except at 0.
That's right.
And so it looks more like square when you come down here. But then it rises faster. So the concavity right at 0 is 0, whereas with x squared, it still had a concavity of 2 there. It had a nice constant change. This one is more abrupt, stops, more abrupt.
I see.
Okay, next, determine the concavity of y equal 3 plus sine of x on 0 to 2 pi. So that was y is equal to, I forgot, 3 plus sine of x. And we're on 0 to 2 pi. Oops, including the 2 pi. Okay, so let's find its concavity on all the intervals between 0 and 2 pi. What's y prime equal to?
Cosine of x.
Wonderful. What's y double prime equal to?
Negative sine of x.
Right?
Mm-hmm.
So now we need to figure out where its concavity is 0, and then we'll split up to where it's positive and negative.
Okay.
Right? So where is this equal to 0?
At 0.
It's equal to 0 at,
0 and
I'm not sure what to call these things. We'll just
pi.
start putting them on a number line. At 0, at pi,
And at 2.
and at 2 pi, right?
Mhm.
Yeah.
So let's check the point in between. What about at pi halves?
Negative.
Negative. And what about at 3 pi halves?
Positive.
Positive. So this thing is concave down over here and concave up over here. Whatever it looks like. I'll give a rough sketch of what the author has. Since he put a picture in here, here's pi. So he has it going like this. Mark it there. And then at pi it switches to like that. So concave down, concave up.
Okay.
And then concavity of 0 right there. Another intuition for concavity of 0, the tangent line at that point will actually intersect the function.
Why?
Where the concavity switches directions. So notice over here, the tangent function doesn't intersect. Notice over here, the tangent function doesn't intersect. Oops, the tangent line doesn't intersect. Where the concavity of 0 will also be the point where the tangent line intersects.
So
Okay.
Because it can't intersect, or because that's what it does at 0?
That's what it does when the concavity is 0.
Okay.
Anyways, that's roughly what it looks like. So, definition. Definition. A point C comma f of c, it's just cxy, c comma f of c, where the graph of the function has a tangent line, graph of the function has a tangent line, comma, and the concavity changes sign, so it goes from positive to negative or negative to positive, sign, of inflection, or I'll just call it an inflection point. Okay. The tangent line in the definition might be a little bit weird. What does a tangent line mean for us? It means the function is defined there, and it has a derivative there. So if the function is defined at a point, has a derivative at that point, and the concavity changes sign, it's an inflection point.
What does inflection mean?
Inflection meaning it's changing.
Okay.
Changing, so the concavity is changing either from positive to negative or from negative to positive.
So is the point where it changes the inflection?
Yes, so we just we're looking at something like this. This was the inflection point.
Okay.
It's the point where the concavity changes. And all this business about there being a tangent line at that point, that just means the point of the function is also defined, so you can talk about that point, and the derivative exists at that point. Oops. Didn't really draw that very well, but that's all that knows.
How do you know what kind of slope the tangent line has?
Doesn't matter. But you calculate the derivative at that point. That's how you get the slope of the tangent. Could be 0, could be some other number. Okay. Let's see his note here. At a point of inflection, either the second derivative is equal to 0 or the second derivative fails to exist. Okay, so same way when we were calculating what we call critical points for derivatives, we were looking for where the derivative was 0 or where it didn't exist.
Yeah.
Similarly, when we're looking for inflection points, then we're looking for where the second derivative is 0 or the second derivative doesn't exist.
Okay.
Same thing we were doing with derivatives, it's just now second derivatives. And same way we talked about critical points, now we talk about inflection points. Okay, so let's do the next example. I hate when he doesn't word it as a question and he just gives a bunch of explanation. So, example, we're looking at the function f of x is equal to x to the 5/3. That's what we're looking at. And rather than trying to figure out how to word that as a question, let's just start doing an analysis of it. So f prime of x is equal to what?
5/3 x to the 2/3.
And then f double prime x is equal to,
What is that? 10
10
thirds?
10 ninths.
Sorry.
X to the power of -1/2.
right? Something like that.
Yeah.
Okay. So let's calculate inflection points really quick. Where is the second derivative equal to 0?
When x is 0.
It's not. Second derivative is never equal to 0. Where is it undefined?
Oh, when x is 0.
Yeah, so x is 0 is going to be one of our inflection points. So now let's just read what the author's saying and see if we figured out what he wants. The graph of f of x equal to x to the 5/3 has a horizontal tangent at the origin because has a horizontal tangent at the origin. Okay, so we found our critical point.
Yeah.
So now let's look for the tangent line to that point, whatever this function looks like. In other words, what's the derivative at that point?
Derivative at 0.
0.
Which is 0.
Just 0. So that's what he's saying there. So he says the graph has a horizontal tangent at the origin because the derivative is 0 at the origin at 0. So notice it goes through the point 0, 0, and it has a horizontal tangent there. So right here, it's going to look like this. It's going to be flat there.
Because this is the first derivative or the second derivative?
The first derivative is 0
Okay.
at the origin. So it has a slope of 0 at the origin. Let's just keep looking at concavity for a second. What happens when we plug in negative numbers to this thing?
It'll end up negative.
we'll end up negative, and if we plug in positives, we end up
Positive.
positive. So we know it's going to be also concave down over here, concave up over here.
Okay.
So roughly, we know 0 slope there, but then concave down, and then 0 slope there, but concave up. Something like that.
Gotcha.
So that's roughly what it's going to look like. So notice that the second derivative wasn't defined at that point, but it's still an inflection point.
Okay.
So I think that was the whole point of that exercise. Next exercise. The curve y equal x to the 4. Let's do an analysis of that. Oh, we kind of already talked about this one, didn't we?
Yep.
The point is going to be there's no inflection points. So y equals x to the 4, that's something that looks more like this. Get our origin, or our coordinate system on there. So f prime of x, we know is equal to 4x cubed, so negative on this side, positive on that side. F double prime of x, we know is equal to 12x squared,
Which is just positive.
which is just positive. Except for 0 at 0. But the sign doesn't change.
What does that mean?
The concavity to the
change.
left, so
Yeah.
if we draw this, 0, over here we get positive numbers, over here we get positive numbers.
Okay.
It's only inflection if it changes.
So yeah, it's only inflection point if it changes signs as well. So just because you found a place where the second derivative is 0 does not mean you have an inflection point. You also need to check that it actually changes sign there.
Okay.
And you're only going to find inflection points where the second derivative is 0 or undefined.
Correct. So if the second derivative is 0 or undefined, you may have an inflection point,
Okay.
but it's not guaranteed.
Okay.
Here's an example. Okay, next one. The graph of y equals x to the 1/3. So let's do an analysis of that. Y equals x to the 1/3. What's that roughly going to look like? Is that like this? I think. Yeah. Because it's the inverse of x cubed, right? So I was trying to draw a cubic on the side. That didn't really come out well. But I think you get the point. This should be increasing and then increasing. So it should be increasing the whole time.
I see.
Okay. Anyways, so f prime of x, what do we get?
1/3 x.
1 over 3 x to the 2/3, or 1/3 x to 2/3, same way you thought about it, right?
Yeah.
Okay, so notice when we plug in 0, what do we get?
0 undefined.
Undefined. So this has a tangent slope here, if I would have drawn it right.
Ouch.
An infinite slope,
Do you
if
get
you want to call it that. Talk about the derivative right now, not
right.
the second derivative. So right here, the slope is undefined, because it's supposed to be straight up.
Okay.
So I probably should have given it more like that. Anyways, which makes sense, because remember the derivative of x cubed was 0. So 1/3, the derivative is going to be straight up and down. Anyways, let's look at f double prime of x now.
No.
Negative 2 over
Nines.
9
What?
x to the minus 5. 5? Yeah, 5/3.
5/3.
Okay, so notice this is going to be negative when we plug in negatives. Oh wait, other way. This will be negative when we plug in a negative, so the whole thing will be positive when we plug in a negative.
So when we plug in a positive,
We
it'll
should get
be
negative.
positive.
Positives should give us negatives, and negatives should give us positives. Look, let's
No.
plug in a number. Let's
Plug
plug in 8.
8. Yeah.
8 is a positive, so we're going to get a negative out of this.
Yeah. Times another negative.
Now, what's 8? What's cube root of 8?
2.
2 to the power of 5, 32.
32.
So this whole thing is 1 over 32.
What happened to the negative though?
That just means it's in a denominator.
Oh.
Oh, that's what's throwing you. Okay. Yeah, remember this just moves it to, okay, maybe I should have done this. Which is the same thing as negative 2 over 9 times x to the 5/3. And then
Okay, that helps way better.
Okay, so. I thought I did that because I did it up there. Okay. So there we go. So now we see you plug in positives, we get negatives. You plug in negatives, we get positives.
Mm-hmm.
So what does that mean? That means from negative infinity to 0, it is concave. When we plug in negative numbers, we get positive, so concave up,
Yeah.
right? So it better be a piece of a smiley face.
Yeah.
And then from here onwards, it's concave down, we got a piece of a frowny face.
Yep, that's right.
Good?
Mm-hmm.
Yeah.
Okay. Last example, one working with position, velocity, and acceleration. Okay, concavity gives us acceleration. If the curve that we're talking about is a position curve. The slope of a position curve is velocity, the slope of a velocity curve is acceleration, so the concavity of a position curve is acceleration. So, I'm going to ignore the book for a second and just do some basic physics with you now for a second. So, we know that if I throw an object through the air, that's projectile motion, and it creates a parabola. That's why it's called projectile motion. So if I throw this through the air and we carefully mapped it, it maps out a parabola.
Okay.
So, maybe I don't want to do that because it won't come out perfect. Maybe it will. It's going to be an upside down parabola, though, right?
Mhm.
Facing downwards.
So it's negative.
So it's going to be negative. So S of t is going to be, I'll just give you the actual equation and then we'll go from there. X naught plus v naught t plus 1/2 a t squared. Okay, here's what maps out the actual position of an object with respect to time. Giving its x position, I'll call this x. Okay, or we'll actually call this y, because we're thinking about throwing it through the air. Think about throwing this through the air, whoop, right?
Mm-hmm.
And so we'll call this y naught. Here's what it comes out to. Y naught is just the initial height I throw it from. So if I start at 1 meter off the ground, that's what this is. V naught is the initial velocity I give it.
Okay.
And then acceleration is acceleration,
I see.
which in the case where I'm throwing this marker is going to be gravity.
Yeah.
So gravity is roughly negative 10 meters per second squared, because it's down. So when we're talking about gravity, replace a with negative 10, this whole thing becomes a minus 5. Everything? So if we were to plot this thing, I don't know exactly what it would look like, but it would look something like, it's going through the air, let's pretend it starts out at a height of 0, so it starts out like this, and then depending on how much velocity we give it, the object looks something like that, right?
Mm-hmm.
So notice that that is always concave down because the acceleration is always negative on that interval.
That makes sense.
So you can tell just from the curve of the position curve, what the acceleration is going to be on that object, what the acceleration was. So when you see that, you know that the acceleration must have been negative the whole time because the entire thing is concave down. Okay, now let's look at his example. That was probably too much of a tangent. I realized as I started that it needs more explanation than I thought. So, his example, here's the position of a particle, S of t is equal to 2t cubed minus 14t squared plus 22t minus 5 for t greater than or equal to 0, so going off to infinity. Now, remember that this is straight line position. So when you plug in 0, I start out at negative 5 meters away from where we're calling 0.
Mm-hmm.
When you plug in 0 there, right?
Yeah.
And then after 1 second, I don't know what comes out after 1. Let's pretend it comes out at 10. That means I've now gone over here to 10. Then maybe at 2 seconds, it's back to 0, so now I gotta go back to 0. So we're talking about a particle moving back and forth in a straight line.
Okay.
And this gives you its position after t seconds.
Okay.
Just keep track of what this is talking about. This is talking about straight line motion. Motion back and forth down a straight line. Okay. So there's s of t. So what's the velocity of this function?
6t squared.
6t squared minus 28t plus 22. And what's the acceleration of this function?
12t,
minus 28, right?
Mm-hmm.
So, I don't know. This is also the same thing as, let's factor a 12 out of there really quick.
Can you factor 12 out of 28?
Yeah, it's just going to come out with a fraction.
Okay.
So, when we factor out a 12, we'll get t minus 28 over 12. 28 over 12 is the same thing as 14 over 6. When you divide both by 2, or 7 over 3, 7 thirds. So divide both by 4, minus 7 thirds. Just so you can real easily see when this is going to be 0, right?
Yeah.
And let's look at this one really quick and see and factor it. They really didn't give us nice numbers. Why didn't they got like 24? T minus 28, yeah, I did that. Oh, they just factored out 4. Let's see, when they factor out velocity, let's just do it. Pull a 2 out of here, what do I get?
You got 3t squared
3t squared minus
14t.
14t plus 11, right? And let's erase that, we'll redo that one. Need more space. So this is equal to 2 times, let's factor this, we're going to get 3t times something, t times something. Let's see, these two, when they're multiplied together, have to give me 11. So that's pretty much
number.
That's just 1 and 11.
1 and 11. So if we do negative 11 here, and then added together is negative 14. Okay, there we go. So 3 times negative 1 is negative 3. Negative 11 times t is negative 11. So with negative 3 minus 11t is minus 14t.
Oh, wow.
Okay. So now let's do a of t, and we'll also keep it with whole numbers like that. So a of t was 12t minus 28, right?
Mm-hmm.
Which was equal to, just factor out the 4, and so we'll just leave it as 3t minus 7. Leaving all fractions out, right?
Yeah.
So Vt equals 0 at t equal to, when is that going to happen? At 11 thirds. You see that?
And 1.
And 1. So that's where my velocity is 0. My acceleration, a of t, is going to equal 0 at, where does that happen?
7 thirds.
At t equal to 7 thirds. Not sure what we're even supposed to be finding here. Let's read the problem. A particle is moving along the horizontal coordinate line, following that function. Find the velocity and acceleration and describe the motion of the particle. Describe the motion of the particle. So, I guess we can talk about where its velocity is positive, negative, and then where its acceleration is positive, negative. So, let's just keep doing similar analysis to like what we've been doing. So V of t, our interesting points are 1 and 11 thirds, and then 0, because that's where we're starting.
Yeah.
So we'll do 0, 1, and over here we have 11 thirds, right?
Yep.
That's all places where the velocity is 0. So let's check a point. What do we get when we plug in 1/2 to our velocity function? So our velocity function, that's right here. If I plug in 1/2 here, I get a negative, right?
Mm-hmm.
If I plug in 1/2 here, I get a negative.
Yeah.
So the whole thing comes out positive.
Okay.
With me on that?
Yeah.
Okay. Let's see, when we plug in a number bigger than 1, but less than 11 thirds, so let's plug in 2.
Negative.
Huh?
It's a negative.
When we plug in 1/2?
No, for 2.
No.
Oh, when we plug in 2. Okay, so this one comes out positive, this one comes out negative, and so overall it is negative. Okay, let's plug in something bigger than 11/3, like 12/3, which is 4. So plug in 4. What do we get?
Positive, positive.
So here we have positive velocity, 0 velocity, negative velocity, 0 velocity, positive velocity. So for the first second I'm moving forward, then I stop, I move backwards, until we're at 11/3 seconds, and then I stop and I move forward.
Okay.
To infinity.
To infinity.
To infinity. Yep. Now let's look at acceleration. What do we have? Acceleration, the point that we're interested in is 7/3, wherever that is. So, plugging a point over here, see what our acceleration is.
This one.
Sure, we can plug in 1.
Negative.
Lost that function. Right here, it's negative, so we have negative acceleration here. And then, plug in a number bigger than 7/3, so plug in 9/3,
Positive.
positive. So, I start out with a positive velocity, right? That's up here. Start with a positive velocity, but I'm instantly slowing down. So I start with positive velocity, but I'm slowing down, slowing down, slowing down, stop. Now I have a negative velocity, but there comes a point where I have a negative velocity that I start speeding up. So my negative velocity slows down until I stop, and then I keep speeding up forever this way.
How does...
The acceleration is negative, so it's like I put you in a car and I push the car, right?
Okay.
So you start out with a positive speed. You instantly start hitting the brake, right? You hit the brake, you hit the brake, you hit the brake. You're finally to a stop. That's not good enough for you, so you actually decide you're going to start reversing. You're reversing, you're reversing, you're reversing. Then you're like, wait a second, I want to go forward. Well, sucks that we have brake and accelerator. Let's think about if you just had 2 pedals. One is I want to speed up that way, the other one is I want to speed up that way.
Okay.
So you have your backwards, I want to go backwards pedal, and I want to go forwards pedal. And if you hit your I want to go backwards pedal when you're going forward, it has to bring you to a stop, then start going backwards. Right? So here you're hitting your I want to go backwards pedal, here you're hitting your I want to go forwards pedal. So I start by throwing your car, you instantly say, no, I want to go backwards, I want to go backwards, I want to go backwards. Here's where you stop, and you start going backwards. And now you're going backwards pretty fast, and then you decide, actually, I hit my I want to go forward pedal. So now you're still going backwards, but you're hitting your I want to go forward pedal, so you're slowing down, slowing down, slowing down, stop, and now you're going forward, 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 forward.
How does...
Okay.
What does
I like that.
and turn back?
Here is where you
Acceleration
stop at
has-
1 second. Your velocity is 0, not your acceleration.
How
Your
does-
velocity is 0.
How do you have an acceleration if you're stopped?
So imagine you're running this way, and I bring my fist into contact with your face. Your face stops, then starts going that way. Your face was accelerating that way the whole time. Once it came into contact with my fist, right?
Yeah. So it's just instantaneous.
Well, not instantaneous. There's going to be some time where it absorbs you. You can imagine that you got one of those big tubes around you. So I make contact with the tube. It first starts slowing you down, stops you, then starts pushing you back. So you can have a positive or negative acceleration and not be moving. That's perfectly fine.
Yeah.
That's the same thing as your function has a positive slope, but it's crossing the x-axis. It's 0 there. If I were to graph your derivative function, that's just where it crosses the x-axis.
Okay.
So perfectly fine to have positive acceleration and not be moving. You will be moving, for sure, shortly. It's just right at that instant. Okay. So, did a nice physics example. Talked about that.
Those physics examples, they solidify it a lot better.
Okay, now they want us to do a sketch the graph. So, we're we're going to sketch a graph by looking at where it's increasing, where it's decreasing, where the derivative is 0, and what the concavity is doing. We're going to be using all this, putting it all together to try and sketch a graph.
Okay.
Okay? So this will be a pretty common problem. So we have f of x is equal to x to the 4 minus 4x cubed plus 10. Right?
Okay.
Yeah.
Okay. So first thing I want to do is take my derivative. It's going to be 4x cubed minus 12x squared, right?
Yep.
Which is equal to factor of 4x squared out of everything. That. Maybe we'll do our number line here and then we'll go on to the second derivative. So point of interest, 0 is a point of interest, right?
Yeah.
So 0 at 0 and 0 at 3. So let's see what's doing in between.
Okay.
So if we plug in -1, do we get a positive or a negative?
You get a negative.
Right. If I plug in 1, what do I get?
Negative.
Still negative. And then if I plug in 4, what do I get?
Positive.
Positive. Okay, so it's decreasing over here, increasing here.
Okay.
Whatever the function's doing. Okay, now let's look at f double prime of x. The concavity.
12x squared
Okay.
minus 24x.
So let's factor 12x out of that. That's the same thing as 12x times x minus 2. Did I do that right?
Yep.
Okay, so let's look at the concavity. Where's the concavity? 0,
0.
And
0, and 2. What's it doing at -1? Or positive or negative?
It's a negative.
No, it's a positive.
This is negative, and so the whole thing's
Wow.
positive, right? So now let's plug in 1, what do we get?
Negative.
Positive, negative gives us negative. And then let's plug in 3, what do we get?
Positive.
Positive. So it's concave up, then concave down, then concave up. Right?
Yeah.
Okay, so now let's do a rough sketch of this curve. See if he has a picture of it so I can get my number line roughly right. So down to -20 up to 20. Okay. And we don't need to worry about too much in the negative direction since both these start at 0. Right?
Yeah.
Typically, so I looked at his to try and get a feel for what scale I'm going to look at, but just plug in a couple numbers to get a feel for what your scale is. Or your extremes, your maxes and your mins. So maybe we should have just done that. Let's just do that for a second. So let's look at f of 0 and see what that's equal to. 10.
10. Yep.
Let's look at f of 3, see what that's equal to.
Well, it's 3 to the 4.
What's 3 to the 3?
27.
Times 3. Okay, 3 to the 4 is the same thing as 3 squared times 3 squared. I mean, that's easier.
-1.
There you go. So we have 81 minus,
4 times 27.
or 12 times 9, if that helps you.
108. Plus 10.
So what does that come out to?
Uh,
19.
No.
no.
First off, it's negative.
17.
Oh,
Right.
that's easy.
Yeah.
Okay, so negative 17. And notice that negative 17 is going to be a min. Right?
When x is 3.
Decreasing and
Yeah, when
increasing.
x is 3.
Yeah, so negative 17, this is going to be one of our mins. So let's start putting points in here. Ooh, that was a bit much. We'll call that negative 20. So we'll call this negative 10. So those will be 5s. Anyways, so over here at 3, we have this scale really stretched out and this really compressed, but those matter. So over here at 3, we're down here at negative 17, right?
Mm-hmm.
Something like that. At f of 0, we are at 10. So this is really going to shoot up here, isn't it? So at f of 0, we were at positive 10. Let's see. We're decreasing, we're still decreasing here. So we're decreasing on this whole interval, right?
Yeah.
But we're concave up from negative infinity to 0, and then concave down from 0 to 2. So we're going to be concave down here from 0 to 2. So let's find these points. We didn't find these points yet. We know f of 0, what's f of 2? That's what we're missing. 16 minus 32 is negative 16, plus 10 is negative 6. Did I do that right?
Yeah.
So f of 2, we're over here at negative 6. Like that. And that's going to be where our concavity switches, right? So we're concave down here. We're concave up here. And we're concave up here. Concave up, so like a smiley face. Then concave down, so like a frowny face. Then concave up to infinity. We're increasing from 3 to infinity. We're decreasing from 0 to 3.
Yeah.
And we're decreasing from negative infinity to 0.
Okay.
So there's a rough sketch of the curve based off of the information we have.
I see.
Feel like you could do something like that?
Yep.
Mm-hmm.
Okay. I don't think we need to do more sketch the graphs, but he does a lot of them. Let's do the one with the trig function in it. Really kind of class today. Okay, so we'll do one more sketch graph, then move on to the next section. So this sketch the graph, we're doing cosine of x minus root 2 over 2 of x. So that's an interesting one. So we're looking at, look at the derivative. Tough one. Cosine of x minus root 2 over 2 of x over 0 to 2 pi. Okay. So our job, sketch this curve, right?
Yeah.
On that interval. So first off, we're interested in f prime of x. What's that going to equal?
Sine.
Negative sign
Negative sign.
of x. What is that?
That's just a constant times x.
Oh, so the constant minus the constant.
Minus root 2 over 2. Right?
Okay.
Mm-hmm.
Okay. Now, let's see where that's 0. So I want 0 equal to negative sine of x minus root 2 over 2, right? I want to see where this is 0.
Yeah.
Well, that's going to be where sine of x, maybe you can follow me just straight to this, is equal to negative root 2 over 2.
Yeah.
Plus root 2 over 2 to both sides. Divide both sides by negative 1.
Yep.
Okay, so where is sine of x equal to root 2 over 2?
It's at they're both at the force. They're on the bottom half.
At
It's
3 pi quarters.
No,
No.
it needs to be down.
That's right. 5 pi quarters.
Right. So we have 5 pi fourths
And 7 pi fourths.
and 7 pi fourths.
That's right.
So that's going to be where the derivative is 0. Maybe I should put the pi on there so we can keep track of what exactly the points were. And then 0 to 2 pi, those are endpoints. So let's just calculate those while we're here. So what is f of 0?
0.
0. 1 minus 0.
Oh, I see.
Okay.
Yeah.
Yeah, okay. So now let's look at f of 5 pi fourths. What is that equal to?
Cosine of 5 pi fourths is,
Root 2 over 2.
no, negative root 2 over 2.
Negative root 2 over 2.
Minus.
Root 2 over 2, 5 pi quarters.
Yeah, so we'll say 5 root 2 over 8 pi. Okay?
Okay.
Or should we factor some stuff out?
Can we factor it out?
Well, we could rewrite that as if we want to take get a common denominator of 8, we could do that. So that's the same thing as negative 4 root 2 minus 5 root 2 pi over 8, which would be the same thing as I don't know, that's worth it. We'll just think about it as we do it.
Okay.
Okay, so there's f of 5 pi fourths. Let's do f of 7 pi fourths.
Root 2 over 2
Positive root 2 over 2.
minus 7 root 2
Pi.
over 8 pi.
Yeah, right?
Yeah.
Okay. What a mess. We calculated those points. Let's see. Increasing or decreasing, that's what we're missing. Okay, so plug in a point in between, so plug in like pi for our derivative function. Plug pi into our derivative function, what do we get? Negative or positive?
Negative.
Negative. Now between these, plug in something like 3 pi halves.
Positive.
Positive, right? Because this comes out positive 1, this is less than 1. So 1 minus a number less than 1 is positive. And then finally, something in this interval, so something slightly less than 2 pi.
11 pi 6.
Yeah.
We'll just see it comes out negative. Because close to 2 pi, this is basically 0. So we'll just have that. Okay, so negative, positive, negative. Increasing, decreasing, increasing. So now let's look at f double prime of x.
Just negative cosine.
That's nice. So let's look at where it's 0.
Pi and 3
Not
pi.
pi.
I mean, pi halves and 3 pi halves.
Pi halves. Oops. Pi halves and 3 pi halves, right?
Mm-hmm.
Okay. So that's where it's 0. So let's look at f at pi halves. What do we get?
Cosine of pi halves is just 0 minus root
Oh,
2.
we're up here.
Yeah.
0 minus, so we have negative root 2
Times
pi
pi.
over 4, right?
Yep.
And then we need f of 3 pi halves. So what do we get?
Just negative
3 root 2 over.
Negative
Four
3 root 2 pi
pi over
over
4.
4. Alright, let's sketch this monstrosity. See what it looks like.
Oh, fun.
Are we almost always negative? we're positive and negative, we go up to 1. How far down do we go?
Couldn't tell you.
Plug in 2 pi to this really quick. So find f of 2 pi. That's going to be equal to, cosine is going to be
1
1
minus,
root 2 times pi. Right?
Yeah.
yep,
So root 2 times pi, what does that come out to roughly? Just get a
Well, that's
calculator.
1 minus root 2 times pi.
Yeah. So we can approximate that, and we know what root 2 times pi is. So root 2 times pi is equal to roughly 4.5.
4 and 1/2. So 5 halves.
I think my battery just died. How again? So 4.5, so gets down to roughly negative 3 halves, right?
Yeah.
So we have 1 here, we'll do our x-axis here. 1, 2, 3, 4. So you guys apply your calculators. You got a calculator?
Mine's also dead.
Do you have a calculator? Are you gonna have to use Google?
Yeah.
Goodness. You guys are killing me. To get some approximations on these things, or maybe the author already has them right now. Okay, anyways. So let's start applying the scene. So f of 0 we know is 1, right?
Yeah.
And then let's see the points that we're interested in on here. We'll just divide this thing up. So we'll call this 2 pi. So we'll call this pi. So this right here will be 3 pi halves. This right here will be pi halves. And then we'll plug in points of interest in between. I guess we could do the force. Here's all the force. That seemed to be what we cared about. So, let's see. F of 0, f of 5 pi force. Jeez, I don't know. So we've got. So we've got square root of 2. Square root of 2 divided by 2 plus 7 root 2 times pi divided by 8.
It's a minus.
Seven root 2 divided by 8 times 3.14. Okay, 4.6. So when you make that negative, negative 4.6. So that was at 5 pi force. We're roughly negative 1, 2, 3, 4.6.
That's
So somewhere like right there.
for sure. Didn't you put 7 root 2 over 8?
Oh,
That's what you were saying.
oops. I looked at both of those. Some, yeah.
So I'm
Alright.
typing it away.
So that positive, that negative. So we jump clear ahead to the end, which is negative 3.2. So over here, this is one we just did, right? 7 pi force, 1, 2, 3.2. I don't know how you guys are going to do your homework without calculators.
I mean, you use Google as well.
Okay, next one. It'll be easier just write the functions and put them in. I'd rather do it this way. We have negative square root of 2 divided by 2 minus 5 times the square 2 times 3.14 divided by 8. Okay, that one's negative 3.5. So over here, we have 1, 2, 3.5. Roughly, right?
Which one did you do?
This one.
5 quarters.
Let's really quick figure out which one of these was a local min. That one was a min, right? Negative, positive, negative. So this is going to curve like that around there.
That's not 5 by 4s.
That is 5 quarters.
5 pi fourths.
I'm saying on your graph.
Oh, what am I doing? Yeah, it's over here. 5 pi fourths, right?
Yep.
So that's going to be a local min. Not really sure how good I'm plotting these. Local min, so it's going to curve up like that right there. Let's see. 3 pi halves, did we plot that point? Yes, we did. So that one is equal to negative 3 times square root of 2 times pi, all divided by 4. So that's negative 3.3. These numbers are way too close.
7 pi quarters is
Still.
supposed to be a local max.
Huh?
7 pi quarters is supposed to be a local max. It's basically the same thing as the minimum.
Yeah, let me just look at the author's picture because, yeah, so here's the picture roughly. You see how it's hardly even curving?
Yeah.
Yeah.
Yeah, so with our rough plots, we're not going to see this hardly even curving. So, yeah, we'll just do it based off of what we know about the point. So this point right here is 5 pi fourths. Oops. Yeah, 5 pi fourths. This right here is 7 pi fourths, right?
Yeah.
Okay, so we know that 7 pi fourths should be a local max, right?
Mm-hmm.
So whatever it is, it's curving away like that there. Local max. Then we know 5 pi fourths should be a local min. So it curves away to 5 pi fourths where we have a local min. And then it's going up. Is it increasing the whole way from there? So from here to here it's increasing. But what's the concavity on it? So our concavity, oh, we never filled out our concavity.
We did not.
So really quick, let's fill out our concavity. Pi fourths, we get negative, right?
Mm-hmm.
Pi, we get a positive, right?
Yeah.
And then 7 pi fourths, we get negative. So there's our concavity.
Okay.
So we're concave down until pi halves, but still decreasing. So concave down till pi halves. Now we're concave up, but still decreasing until we get to here, right?
Yeah.
And then we're still concave up until we get to 3 pi halves, so it's still concave up, and then this is where we switch to concave down again.
Yeah.
Sorry, that's a terrible example for me putting there because of how close all those numbers are together. It needs to pick graphs that jump more. So that was not worth the time I went through it. Okay, last section. The hardest section. But the one where there's nothing new. So, last section, not teaching anything new, just now introducing to you hard problems. Harder problems, more interesting problems. So the first problem is, we have a box. Piece of cardboard. And it's 12 inches by 12 inches. Okay?
Okay.
Our job is to construct a box from this, folding up the sides. So I'm going to cut out from here, x, x, and from here, that same x, x, and from here, x, x, and from here, x, x, to fold up the sides and create a box. You with me so far?
Yeah.
Our job is to figure out how we can do this to maximize the volume.
Okay.
So we want to create as much volume as we possibly can. Right? Now notice right out the door that x, what's the biggest x can be?
6.
6. Can't be more than 6 inches, otherwise we're out of cardboard space, right?
Yeah.
And notice that if x is 6 inches, our volume is going to be 0. And that if x is 0, then our volume is going to be 0. So we need something in between. Anyways, so what's the volume of our function? It's just length times width times height, right?
Yeah.
So this side length is going to be 12 minus 2x. You see that?
Mm-hmm.
Yeah.
And that's also going to be this side length. So length times width, and then x is my height.
Okay.
Oh, I see.
Okay, so now what is the change in volume with respect to x?
2.
So should we multiply this out first?
Yeah.
Let's multiply this out. 144 minus 12 times negative 2 is 24. Doubled is 48. X plus 4x squared all times x. Right?
Mm-hmm.
No. Doesn't the negative 2x, when you multiply it through, cancel out the other one?
Negative 2x is that. Negative 2x times 12 is negative 24x. 12 times negative 2x is negative 24x. And together you get negative 48x.
Oh, I see.
Okay, so finally we have 144x minus 48 x squared plus 4x cubed, right?
Yeah.
So now dv dx is equal to, I'm going to write it in the other order, 12x squared minus 96x plus 144. With me?
Yep.
Yeah.
See if the blue marker is better. Okay, so now if we plot the volume of this thing, I don't know what it looks like. I know it's 0 when x is 0. And it's 0 over here at 6, and so it does something like this in between, right?
Okay.
So we want to figure out where it's maximized. So we want to know where its derivative is 0.
Okay.
So where is the derivative of this equal to 0 is the question that we're trying to answer.
I see.
Okay, so I want to know where 0 is equal to, let's factor 12 out of all this. 12x squared minus, what do we get when we factor 12 out of that?
8
8x
plus 12.
plus 12. Right?
Mm-hmm.
So I want to know where that is equal to 0. Well, that's going to be where this is equal to 0, because this is never equal to 0. We're dividing both sides by 12, right? So 0 is equal to, let's factor this, x times, we can leave the 12 there. We'll just factor this piece right here. Okay, x, what is it? Added together gives me this, multiplied, other way. Multiplied together gives me this, added together gives me this.
4.
No?
No.
Other one.
6 and 2.
6. So minus 6, x minus 2 is where the derivative is 0.
Mm-hmm. It's at 6 and 2.
At 6 and 2, but we know 6 isn't the one we care about, so 2 has to be the one we care about.
So when x is 2?
So when x is 2,
2 inches.
2 inches. So cut out 2 inches from both these to maximize the volume. So if you were working in a little shop, you need to figure out, how much did I cut out to maximize my volume? There it is.
Everybody's going to wonder why my boxes are a little bigger.
Yeah, how come Jeremy can get these boxes just perfect to hold the most volume? Okay, so now we're doing another one. You have been asked to design a 1 liter can. 1 liter is roughly 1,000 cubic centimeters. Well, it is 1,000 cubic centimeters, so keep that in mind. Okay. So 1 liter can shaped like a right circular cylinder. And we want to minimize how much material we use. Okay, so our job is we got to design a soda can. And it has to hold 1 liter.
Mm-hmm.
We want to minimize the materials. We don't want to use more materials than we need to. So we're going to try and minimize the surface area.
Okay.
Okay. So we know what the volume is. We need to minimize the surface area. So really quick to make sure we're all on the same page, draw a cylinder. So a circle comes down, like that. We need some dimensions on here, call that R, and we'll call this H.
It's a big soda can.
Now, what is the volume of the soda can? How do we calculate the volume?
Of a cylinder?
Yeah, area of the base times the height, right?
Yeah.
So that's pi r squared times h.
Okay.
Okay. Now, what about the surface area? So we know that we want this to equal 1,000. That was given us, right?
Yeah.
It's going to be, assuming everything's in centimeters, because then 1,000 cubic centimeters is what here. So we'll keep all our dimensions in centimeters. So now, what's the surface area of the zinc? We have a circle on the top and the bottom, so we have 2 pi r squared for the 2 circles,
Okay.
right? Plus, we need the area for the part that wraps around now, right?
Okay.
So that's going to be the same as, imagine unwrapping that. If we unwrap it, this is h, what's this distance right here?
Circumference.
Circumference, 2 pi r,
Oh, what the heck?
right?
Okay.
So 2 pi r times h. Okay, now here's where you, hopefully if you read this problem, you can kind of get this far. And then here's where you would most likely get stuck. You want where, you know that you're trying to minimize the area, so you're looking for a minimum. So whatever the graph looks like for your different dimensions, it's going to look like something like that. We're trying to find a minimum of the area. But we have 2 variables in here. We have r and h.
Yeah.
So what do we take the derivative with? That's where you come back up here and look at the information that you were given. This will allow you to rewrite r in terms of h or h in terms of r.
Oh, so it doesn't matter which one you try?
Yeah, it doesn't matter which one you do.
Okay.
So 2r squared times h equals 1,000, or in other words, h is equal to 1,000 over pi r squared. You see that?
Yeah.
Now if I come do that substitution down here, I'll only have an equation with r's. I can differentiate with respect to r, look for where it's 0, and find the min.
Okay.
Okay, so we know that a is equal to 2 pi r squared plus 2 pi r times h. With me?
Yeah.
Which is equal to, we still have 2 pi r squared plus 2 pi, well, pi is being canceled out with pi, 1r is being canceled out with 1r, 2 times 1,000 is 2,000, over
R.
r. Wonderful.
Now we can find the derivative.
So now, the derivative of a with respect to r is equal to
4 pi r.
4 pi r, sorry, that's a 4, pi r.
What is the derivative of that?
Come on. That's the same thing as r to the minus 1. You got this.
So
How
that's
is it?
negative 2,000 r power of negative 2.
There you go. R to negative 2 or over r squared.
Okay. Okay.
I'm still lost.
So we have 2,000 r to the minus 1.
Yeah.
Bring down the minus 1, make it minus 2.
Okay.
Good? Okay, so now we're looking for where that thing is 0.
Yep.
Right? So I want to know where 0 is equal to 4 pi r minus 2,000 over r squared. Well, first off, move this to the other side and multiply both sides by r squared. So I get 2,000 is equal to 4 pi r cubed. Follow that?
Yeah.
Okay. Divide both sides by 4 pi. So we get 500 over pi. That's dividing it by 4 pi. Is equal to r cubed.
Then you cube it.
So r is equal to the cubed root of 500 over pi.
Okay.
That's where we're 0.
Okay.
So that's our minimum. And we could get a rough approximation of what that is in terms of centimeters and calculate h from that because we know the relationship of r to h. So, come on. Cube root of 500 over pi, so we got the same number. Where's his approximation for what that number is? .42. It's roughly 5.42 centimeters. Right?
Okay.
So then you plug that back into here, solve for h. And we don't need to do that, but h comes out to roughly twice r.
So our goal was to find the
H
height and the radius?
Comes out to roughly 10.84 centimeters. So if you want to maximize, so if you want a soda can design that holds exactly, if you want a container design that holds exactly 1 liter, and you want to minimize, and you want it to be a cylinder shape, and you want to minimize the materials that you use this as a radius for the top, and this is the height of your can. And it will hold 1 liter.
Interesting.
And that's the minimum amount of material, so you use as little tin as possible, or whatever you're making the can out of. Make sense?
Yeah.
Okay, let's do another one like these. This one is maximizing the area of a rectangle inscribed in a semicircle. That's what it looks like, and our circle has a radius of 2. Okay. So on this one, we have a semicircle. It's supposed to be a semicircle. Has a radius of 2.
Okay.
Our job is to construct a rectangle in here with maximum area.
Okay.
You understand the problem?
Yeah.
And notice that, is it better to pick a point right here for my rectangle, or should I go up higher? How high up should I go? What gives me the most area? Now notice that, if we pick, let's see, so we'll call this distance right here x, this distance from here to here, right?
Mm-hmm.
So our x has to be between 0 and 2, because we have a radius of 2. I erased that. Here, put mark 2 right there. So x has to be between 0 and 2. Okay, so we're trying to maximize the area. If we call this x, what's the height of this thing going to be?
The sine of...
Let's draw the triangle over here for a second. Sorry, terrible drawing of the triangle. But that's this triangle, right? This side length we know is 2, since that's the radius of the circle.
Mm-hmm.
If we call this x and this is 2, what's this? Alright, let's call this y for a second, and what do we know about x, y, and 2?
X squared plus y squared equals 4.
Wonderful. So y squared is equal to 4 minus x squared, or y is equal to the square root of 4 minus x squared, right?
Okay.
So this right here, this distance, is square root of 4 minus x squared. That's this distance.
Okay.
So our area of our rectangle now is what?
X times...
2x.
X times...
Minus the
Oh,
dividend.
2x, thank you. 2x. Good eye. 2x times 4 minus x squared.
Mhm.
That's our area. That's our area with respect to x. We're looking for a maximum now. So take our derivative, dA dx, and what do we get?
2.
Product rule, derivative of the first, multiplied by the second, plus the derivative of the second, multiplied by the first. The derivative of this is going to be 1 over 2 square root 4 minus x squared. So this is the same thing as all that to the 1/2. Bring down the 1/2 and make it negative 1/2. Puts it in the denominator.
Negative 1/2.
Yeah, so let's just look at square root of x. Square root of x, when I take its derivative, I get 1 over, when I take its derivative, I get 1/2 x to the minus 1/2, right?
Mm-hmm.
Which is the same thing as 1 over 2 times the square root of x.
I see.
Okay, so that's the derivative of the outside. Chain rule, so multiply by the derivative of the inside. Let's put the derivative of the inside right here, which is negative 2x. Right?
Why negative 2x?
What's the derivative of the inside?
Oh, the inside.
Okay. So we did derivative of the first multiplied by the second plus derivative of the second multiplied by the first. So that's actually going to be minus 4x squared. All that?
Why?
Yeah.
Negative 2x for the derivative of this,
Yeah.
and 2x.
Okay.
Okay, so there's that. Get a common denominator. So multiply top and bottom of this by that. You with me?
Mm-hmm.
Okay, so this is equal to, when we multiply this to that, we're going to get 4 times 4 minus x squared plus minus gives us minus 4x squared all over 2 square root 4 minus x squared. With me?
Mm-hmm.
Okay, so now we're going to get, that was going to cancel out. I hope I didn't make a mistake. We're going to get 16 minus 4 gives us minus 8x squared all over 2 square roots of 4 minus x squared, right?
Factor out the 2.
Cancel out 2 top and bottom. Good eye. So that's the same thing as 8 minus 4x squared all over the square root of 4 minus x squared, right?
Mm-hmm.
Now we want to know, well, now I need to factor the numerator really quick. So this is equal to, factor 4 out of this gives me 4 times 1 minus 2x squared all over
So
square root.
you have that backwards. 4 minus
Thank
2.
2 minus x squared, right?
Mm-hmm.
All over 4 minus x squared. Okay, so now where is the derivative 0?
When x is 2.
When x squared is 2. Or when x is
Root of 2.
square root of 2.
Oh, I was looking at the bottom, sorry.
Yeah, we don't care about the bottom. All we care about is the top, and we're trying to figure out when it's 0. So 0 at square root of 2. So when x is equal to the square root of 2, our area is maximized.
Okay.
That's what we were after.
Oh.
What's the max? When is our area maximized? When we pick square root of 2 as our x.
Why don't you want to do... No, you're right. You're right.
So see what our max area would be inside the circle. I guess we could figure that out real quick now. So area, our max area is going to be 2 times the square root of 2 times 4 minus 2, right?
Why? 4 minus... You're right.
Okay. So 4 minus 2 is square root of 2 times square root of 2 is 2 times 2 is 4. So our max area is 4. 4 whatever our units were. It's the most area we can fit inside that circle.
Interesting.
Yeah, cool problems, huh? One more with the speed of light, then we'll call good.
Yeah.
Alright. We'll derive Snell's law. Something used in optics and physics. Now what you have to know in deriving this is that the speed, or that light always travels through a medium so as to minimize the time it takes. Light will automatically take the path that minimizes the time that it takes for it to travel through a medium.
I'm still lost with that.
Light will take the shortest path between 2 points. A photon.
Okay.
I throw a photon through a medium. It's going to take the shortest possible path. which is why it bends when it goes through water. And we're kind of showing why it bends when it goes through water. That's what we're about to show.
Okay.
So here's our diagram really quick. And then our x-axis, this is going to be where it switches from one medium to another. Meaning here it's in air, here it's in water.
Gotcha.
And we're going to see how the light bends, basically. So we'll call A, this point, the source that the photon's coming from. Photon's going to come down, hit a point here. He calls the point of impact P. And then it's going to bend based on the medium. Sorry, can't really tell it's bending there. Bend, so it's at a different angle. Can you tell it's at a different angle?
No, very a little bit.
Let me start again. This wire is getting worse and worse. I hate these erasers.
Is it the eraser or the whiteboard?
It's the eraser. It's like a rubbery. I bet that's why someone took the time to find this thing. See? It's getting it off way better. But I'm not going to spend the time to work with that. Let's just move the camera over to this whiteboard real quick and
Okay.
do it over here. Okay. So I'll be trying to be more dramatic with my angles. So here, this line is where it goes from one medium to another. Make this more steep, so it comes in like that. It's the point of impact the author calls P. And then it bends at some other angle. Is that more obvious?
Yeah.
Still not great. Let's do, how's that?
Yeah.
Okay, so then it bends at some other angle. We'll do ends here at some point B, and label some points. We'll call this theta 1, theta 1. We'll call this, so this was point P. We just might need to know also that if you draw a vertical here, I'm not sure if we'll need it, but this angle right here would also be theta 1. I think the author has that in the picture. Yeah, it does. P. Then we call this angle right here theta 2. And we have everything labeled in the diagram that he has labeled. Okay, this distance from here to here we're going to call x. If we continue this down, we just need to mark this point to make triangles. We'll call this point, we'll call this distance d.
Okay.
So this whole, well, no, that's not what he's saying. He's calling this whole thing d, so d is this coordinate. So this distance right here is d minus x, for that distance on this triangle. So x, d, d minus x.
Okay.
Got all those points labeled? He calls this distance right here little b, and okay, I think we're ready to just start writing down some formulas. Okay, first thing to know is that time, when we're solving for time, because I told you that a photon minimizes the time, takes a path that minimizes the time. So you're used to doing the derivative of x with respect to t, we're ultimately going to be calculating the derivative of t with respect to x. It's the time that we're looking to minimize, not the distance.
Okay.
Not the path. Okay, so time, in short, is equal to distance, or, distance over rate. I was saying that right. It's just you hardly say it that way, so it sounds weird. Distance over rate. Gives you time.
Is that a universal definition or just for this problem?
Well, you're used to rate times time equals distance,
Okay.
right? If I'm going 20 miles an hour, and I do that for 2 hours, what's my distance? It's based off of the units, because distance is in meters, rate is in meters per second. When you divide, you get seconds, which is a time.
Okay.
So, anyways, so T1, the time for this path, we can call T1. T1 is equal to this distance, AP, divided by how fast a photon moves in this medium. Light moves faster through in a vacuum than it does through water, for example.
Okay.
So we'll call the photon's speed in this medium up here C1, and then its speed in this medium down here we'll call C2. So that's T1, T2 is equal to PV all over C2, right?
Yeah.
So now our total time is equal to T1 plus T2. And this is what we're minimizing.
I see.
T1 plus T2, which is equal to AP over C1 plus PV over C2, right?
Mm-hmm.
Yeah.
Which is equal to, now let's calculate these things. We didn't put a height here. He does. Little a is this height. Okay, so this height is little a, and then we label this height as b. Okay, so we're good. So, AP then is equal to what?
A squared times plus x squared is...
A squared plus x squared under the radical over C1. And then this distance is going to be
b squared plus d minus x squared in the...
b squared plus d minus x squared all over C2.
Yeah. Yeah.
Okay, so now we're taking the derivative of t with respect to x. Right?
Okay.
So, because, let me try and make sense of this to you really quick. We're trying to figure out the path that the photon takes in going from this point A to this point B. That's what we're trying to figure out.
Okay.
And so once we have our x is figuring out like where it's going to bend and change its path. Because in this medium, it's going to take a straight line, because that's going to minimize the time in that medium, right? And in this medium, it's going to take a straight line, because that's going to minimize its time in that medium. The only question is, where exactly is this x going to be? So let me try and give you an example to make this appeal to your intuition, to help bring the problem to life.
Okay.
Imagine for a second that you have to get from point A to point B. Okay? You do. And let's imagine for a second now. Up here, this is like a pit of mud, which is harder to walk in. And over here, it's kind of just like a pit of water, which is easier to walk in. So what do? Do you hurry up and run down to the water and then run to point B?
No.
Because it's easier in the water to walk through than the mud? Or do you walk on a slanted path to like right here, then run to point B? What's the path you should take so that you get there as fast as possible? Because moving in the mud is slower than moving in the water, right?
Yeah.
Yeah.
So what is that path? That's basically what we're calculating. We're just doing it for a photon.
Okay.
So the photon has two different speeds. Maybe it's easier for it to move through this material and harder through this material. Maybe it's harder through this material and easier through this material.
Okay.
Notice if it was the same for both materials, the photon would just take a straight line right there.
Yeah.
Yeah.
But if it's different for the materials, then it's going to come out different. So that's what we're calculating. We're trying to figure out what this path is going to be. And so figuring out what x minimizes the time is what we want. We want the x that minimizes the time. Or sorry.
I see. Yeah.
Yeah. So that's what we're calculating. That's why we're calculating the derivative of time with respect to x. We're looking for the x that minimizes time, because the x is telling you what the point that you should point towards to then switch to the next medium. Right?
Yeah.
And then everything else is just constants. Okay. So now let's calculate this derivative. So we're taking the derivative of this with respect to x.
That's C1.
So we're going to get, remember, it's a square root, so that's going to be 1/2. So we'll have 2 C1 down here times the square root of a squared plus x squared times the derivative of the inside 2x. Is that too much in one go?
Yeah.
Yeah.
Okay, let's restart. So let's pretend I just have the square root of x over c1, right? That's the same thing as x to the 1/2 over c1. Oops. Right? Take the derivative. It's going to be 1 over 2c1 square root of x.
Okay. But where's the 2x from up there?
Times the derivative of x with respect to x. Chain rule. So now take the derivative of the inside, gives us our 2x.
I see.
Still no?
Where's the...
Okay. Let's just calculate it out by hand all the way. So I have a squared minus x squared to the 1/2 over c1, which is, when I take my derivative, I get 1/2 a squared minus x squared to the minus 1/2 all over c1 times the derivative of the inside. Oh, so negative 2x, oops.
Okay.
Oh, yeah.
Okay,
I see it.
so that is our derivative of our first term. Now we need to calculate the derivative of our second term, right? So this is going to be plus, almost identical. We're going to have 2 times c2 times the square root, times the square root of b squared plus d minus x all squared. It's the chain rule that's going to be harder. We need to find the derivative of the inside now.
Okay.
The derivative of the inside is 2 times d minus x times negative x.
Negative x.
So now this is just the derivative of just this piece.
Oh, I see.
Yeah, chain rules, I chain rules, I chain rules, I chain rule. Chain rules all the way until you get to just an x.
Okay.
Because I could also add on times that times dx dx, which is 1. Okay.
And b squared and a squared are just constants, right?
Yep.
Okay.
B squared's a constant.
B is a constant, so b squared is. A is just how much the distance from where you're starting to the end of the medium. B is just the distance from where you need to enter the second medium to how far down you're going.
So the only variable we're really dealing with is x.
Yeah, x is our only variable. So picture is, here's point A, here's point B, and here's where we switch mediums. We're looking for the path from here to here. What is little a? It's this distance. What is little b? It's this distance. Those are constants, those are given.
Okay.
Make sense?
Yeah.
Okay. So now, simplify. Ooh, that's kind of ugly. No, simplify. Let's not simplify. Well, we'll simplify this and this, the 2's.
You get, yeah.
And maybe, let's see what he simplifies to. T1, T2, he does that. dt dx. So, let's see, simplifying this term, we get negative x over c1 times the square root of a squared plus x squared, right? And then we have plus, looking at this one, the 2 will go out, so we have d minus x times minus x. Oh my goodness, what am I doing? Times minus 1, why did you guys let me leave that there?
What?
What's the derivative of the inside of this? Negative 1. It's not negative x.
Okay.
Okay, so plus 2's go out. If we distribute the negative 1 through, it's going to be that positive and that negative, so x minus d all over c2 times the square root of b squared plus d minus x squared. Right? And let's see the author. The author doesn't have a negative there. and he didn't switch that. So he has d minus x here, keeping the negative sign out in front. That's fine. But he doesn't have that negative. So where did our negative come from?
Negative 2x.
Yeah, it came from that, but why did I put negative 2 there?
Because you went over the problem.
Oh, I think when we wrote the problem down here, I accidentally wrote minus x squared instead of plus. So then I correctly put negative there, which I shouldn't have. Okay. Because the derivative of the inside of this is just 2x, right?
Yeah.
Yeah.
So I bet you that's what I did. Oops. So I wrote the problem wrong when we solved it down here, thought I saw a mistake, corrected up there, which wasn't a mistake. Okay, so now we have the same thing now for this. Okay, no mistakes. Okay, so now, substituting in for the sine of these angles. So, notice that this distance right here, square root of a squared plus x squared. And this distance right here is the square root of b squared plus d minus x squared, right?
Yeah.
So sine of theta 1, oh, sorry. Here's what the derivative is. Now we want where the derivative is 0, right?
Which is just when.
Maybe I'll do a substitution first. So one more way that we can write this in terms of sines. We'll do a substitution, then we'll find where it's 0. So if we write this in terms of sines, sine of theta 1 gives me y over r. Gives me this distance over this distance, right?
Yeah.
Sine of this angle. So sine of theta 1 is equal to x over square root a squared plus x squared. See that?
Yeah.
Sine of theta 2 is equal to what?
D over d minus x over
d minus x
root b's stuff.
over square root b squared plus d minus x squared, right?
Yeah.
Okay, so we're going to do those substitutions over here, and what do we get? This x over a squared plus x squared is sine of theta 1, so we just get sine of theta 1 over c1, which is the speed of light through the medium, minus sine of theta 2 over the speed of light through the second medium. So now if we want where the derivative is 0, if we set this to 0, that's the same as making this equal this, because you move this to the other side.
Okay.
Yeah.
So the derivative is 0, where sine of theta 2 over c2 is equal to sine of theta 1 over c1. So if you know the speeds through the two mediums, c1 and c2, then you can calculate theta 1, theta 2. You can calculate what those angles are that should be used. We didn't have particular angles and particular speeds, so we just solved it in general. So that's called Snell's law.
But if you find the speed, then you can find the angles? Or do you need to get both before you can figure that out?
Do you need to get both before you can figure that out?
I'm saying,
You would need to find the ratio. There's a bunch of different ways to do it.
I'm saying if you know the speed, can you figure that out?
Yes, if you know the speeds.
And you don't need the angles.
No, you don't need the angles. If you know where the points A and B are. But you need your initial points though.
Okay.
So you need the speeds that you can travel through the mediums and your initial points. And then you can figure it out. So that's something that you'll be doing in Physics 2 class, if you ever take Physics 2. Snell's law. Anyways, that's it. That's all we have. I gotta get headed